Great, thank you. Thanks for inviting me at this workshop on learning with complex structure, perhaps intentionally having a vague title. So I decided to, I was sort of debating between speaking about structured probabilistic models or language, and in the end I went with reinforcement learning. So reinforcement learning is the study of how an agent learns to interact with the world to obtain some measure of long-term reward. And it's become one of the standard paradigms for how we think about artificial intelligence. And we've seen a lot of impressive successes recently. Okay, so what is a Markov decision process? So I'll just set up some notation. So we have some agent. The agent's going to take an action at every time step. There's a state in the world, so the agent sees the state, it takes an action. The action is going to manipulate the environment, causing some type of transition to the next state. Okay, and so think of a setting that's episodic. The agent starts in some state, acts for 8 steps, and it repeats. Okay, and the agent's going to see a trajectory, which is a state action reward, then a transition occurs, and it sees the next state action reward, and so on and so forth. And the objective for the agent is to maximize some notion of long-term future rewards. Say, for example, the undiscounted future sum of rewards, when it starts at some state as 0, executes this policy, which is a mapping from states to actions for these 8 steps in the world. Okay, and we take an expectation over the underlying stochastic process. Okay, so that's the notation. If there's any questions, feel free to just interrupt and ask. Okay, so this is just setting the stage. Okay, so what are the challenges in reinforcement learning? Well, we have the challenge of exploration because the environment may not be known. We've got the credit assignment problem due to delayed rewards because maybe we got the -1. We've got to figure out where we made a mistake in a past to assign blame. Okay, and on top of all this, we have this problem of large state and action spaces that make the problem even more difficult. So this is this, as an example, this was this OpenAI demonstration of dexterous hand manipulation. Ignore the Rubik's Cube solver, but dexterous hand manipulation is considered one of the hardest tasks in robotics, and they at least got this thing to work pretty non-trivially to manipulate this Rubik's Cube. And this is definitely considered a very hard controls problem. Okay, and it's surprising how how much progress people are making on the empirical side. Okay, and this thing clearly has an infinite action space. The controls are the forces you apply at each of these actuators. Okay, so that's sort of RL, and let's start with a bit of background and context for how we think about supervised learning, RL, and deep RL. Okay, so we have the classic solution concept here, which is, suppose the world was small. The classic solution concept, if we knew the dynamics in the world, is this tabular dynamic programming approach where, one column we list every possible state in the world, which is uncountably infinite, and the second column we're going to list all possible actions. So this is going to be like the forces applied at the various actuators. And this, these classical dynamic programming algorithms are iterative, that we start with some type of policy and we iteratively improve them by computing some kind of state action value. Think of this as like a greedy one-step look ahead. We compute this value and then we improve it by being greedy with respect to this value we've just computed. And what we're going to do for each entry in that table is compute the value of our current policy in state S, taking action A, and then continuing it. So once we estimate that value, then you can go back and update the policy and repeat. So think like shortest path types of problems. This is the classic solution concept. Obviously, we can't apply this in many realistic problems because the number of states might be large or infinite, same with the number of actions. Okay, so what do we try to do? We try to, how do we try to deal with this infinite table? Well, we often try to deal with this through some type of sampling or supervised learning approach. Okay, and the idea of supervised learning is that maybe we can try to utilize some kind of approximate scheme to figure out the value of how we're doing and to improve it. And this is basically the idea of these deep RL methods. That like deep RL has been, so deep learning has been very, very successful in the last few years in the supervised learning context. And to a large extent, people have just tried to use these methods as function approximators in the RL setting to deal with this large and infinite table. Okay, and it's worked quite well in many, many different settings. Okay, so let's delve into details in one particular optimization methods people use, which are policy gradient methods. Okay, and to a large extent, when you're really trying to get hard problems to work, almost everything is some type of gradient-based method. So this is true in games and in many of the hard control tasks, that you write down some parametric way of parameterizing your policy and run gradient descent to optimize the parameters with regards to your cost function of interest. Okay, so note this, in a sense, completely avoids this, this tabular dynamic programming approach. Okay, so how do they do this? Okay, so why are these policy gradient methods nice? Okay, well, we have this functional form of the policy gradient, which you can write as, so I'm not going to define it formally, but think of these Q values as some type of one-step look-ahead value based on your current policy pi. Okay, and these policy gradient methods are nice for a number of reasons. The first is that you can directly parameterize your behavioral policy, so you're mapping from states to actions. You can just directly parameterize this with, say, some neural network, and we know how to compute derivatives of that mapping. Okay, so this pi of A given S, that's the probability of taking action A given state S. Okay, so that function we know because we've written down, and we can take its derivative. Okay, this Q pi is how good we're currently doing at state S, and this expectation is over the states and actions we visit when we're rolling out pi. Okay, so the second point is we can estimate this gradient using simulations in the environment. Okay, so supervised learning, you don't need to interact with the environment because it's static. You just take your data set and train. But with these policy gradient methods, you can just do Monte Carlo simulations and estimate the gradient. So even though your policy is changing, you'll just, you'll update your policy. Now you're acting differently, but then you'll act according to that policy and get new samples. And as long as you're acting stochastically, you can get estimates of this gradient. And the other nice thing about these methods is, they directly optimize the cost function we care about. Okay, so you just kind of, this is kind of the deep learning pipeline. Try to write down the cost function you're interested in and run it for a long time. Okay, and that's basically what we're doing here. So questions about this approach?
So how do you define the cost function itself? Like you just, like in the look-ahead table, you just said 8. But
so good. So this is going to be like the next slide. So suppose we have some given start state of interest. Okay, so the cost function is going to be, say, the sum of the rewards we get from acting in the world from H steps starting at some given state.
Yeah, I'm guessing, I guess, the rewards, how you define the rewards? Like for the Rubik's Cube?
So in the Rubik's Cube, so this is a good question. So in a lot of questions, so some questions the rewards are given to us by the world. Okay, and in other settings, like in control settings, we'll often define it by hand because we kind of know what we roughly want the agent to do. So in the Rubik's Cube setting, you have some symbolic solver, and you just tell it where you want each finger to go to lock the position down, and then they're going to be, they're sort of not going to be sparse. Okay, and let's come back to this thing, because look, you could just define a reward function which is move one piece to another location. Okay, but now you've got this sparse reward problem because if you drive the thing randomly, you're not going to get any reward signal. Okay, but for now, think about a setting where the rewards are given to us by the world. Okay, so in practice, there is this question of how do we, quote unquote, shape the reward function. Okay, but this is related because let's take a step back and look at the optimization landscape in reinforcement learning. Okay, because we're literally just writing down some cost function and trying to run gradient descent. Okay, and in the supervised learning setting, we don't care about non-convexity. Like practitioners, yeah, it can be non-convex. Who cares? Just write down your big neural network, run gradient descent, everything's fine. Okay, and we don't really concern ourselves with like saddle points. We have these methods like batch norm and resnets that seem to avoid these vanishing gradient problems. Okay, so in reinforcement learning, this picture is very much false. We actually have very, very flat regions, and you can actually show there are problems where the gradients are flat to very high order. So let's just look at a very simple example where this is clear. Just consider an agent which starts at S0, that's the starting state. 2 actions take you to the left, and 1 action takes you to the right, and the reward in the world is 1 state all the way at the right. Okay? So if you just start acting randomly, your gradient is almost 0, because there's an exponentially tiny chance you hit that reward. Okay? And this is true in a lot of these practical settings too. If you drive your robot randomly, it's going to flop around on the ground and not see any reward if the reward is a carrot up at the top. Okay? And this is not avoidable because this is just the structure in the world. Like changing the parameterization of your neural network is not going to fix this problem. Okay, so in many problems, you try to give it little intermediate rewards to help it out, but in some problems, like just the reward is far out in the future. Okay, so that already raises this question that this way we were thinking about the optimization landscape in supervised learning doesn't really reflect what's happening in the reinforcement learning setting, because you might think of this as the lack of exploration will lead to very, very flat gradients. So questions about that? And this begs the question of what's going on, because we are in fact using these policy gradient methods to solve these RL problems. So what kind of tricks are going on? And so how do we think about some of these non-convex issues? But did this partly answer your question about the reward function? So think of it as being given, but it's very much a real question of how we shape them in practice. Okay. But like in these game settings, you're just playing a game or Go, it's if you win or not. Okay. And the question now is look, we're using these policy gradient methods. They're working quite effectively, at least compared to many other approaches. So what's going on? Can we get any kind of theoretical handle on our most widely used tools? Okay, and that's what we're going to look at in this talk. We're going to look at some provable characterization of these policy gradient-based methods. And we're going to look at this basically in 2 regimes. So let's think about settings that are small. So like in this problem, it's a small problem. We might want to understand what's the actual behavior of policy gradient methods in these small regimes. And what about when we start using these methods with things like deep neural networks? Things where the state space is very, very big. We're using some restricted class of policy parameterizations. Okay, so we might like to understand what's going on in those cases as well. Okay, so let's see what happens. And we can actually characterize various global convergence properties of these methods. Okay, so questions about the game plan? Okay, so what's the approach? We're gonna we could write down a policy as a deterministic mapping from a state to an action, but that's annoying for differentiability reasons. So what we typically do in practice is we write down a probabilistic mapping, which is for every state we specify a procedure to act, which is a distribution over our actions, and we parameterize it with some parameters theta. Okay, and by parameterizing it this way, we can take derivatives, we can estimate these gradients through rollouts. Okay, and a very natural way to parameterize things is this parameterization where we say the chance of taking action A in state S is proportional to e to some real valued function of S and A. Okay, so it's worthwhile to look at a couple of different choices of how we parameterize things, and then we'll try to ask what's the behavior of gradient descent in these different cases. Okay, so what's the simplest one? The simplest one to start with is let's just look at the Softmax policy class. So we have a separate parameter for every state and action pair. Okay, and why this policy class is nice is we can represent every possible policy within our class. So we can definitely represent the optimal policy here. Okay, so if we're actually in this tabular case, we might as well just do dynamic programming, but it's very helpful to understand what is the behavior of these algorithms in the simplest possible case where we can represent all policies in our policy class. and we're going to run gradient descent. So we'd like to understand the behavior in this case. And then we can start generalizing this to say, hey, what happens if this is a linear function? So now we have some features in the world, and the chance of taking action A in state S is proportional to this score function. Okay, so some features are known, and theta isn't known. There's another possible parametric policy class. And finally, we could just make this a neural network. And that's basically what we do in practice now. We just make this function some neural network parameterized by theta. Okay, and then we just try to run gradient descent to optimize these parameters. So questions about the setting? Okay, so let's just start with this tabular policy class. Okay, and let's look at what happens if we're going to run this gradient descent algorithm over this class of policies. Okay, so rather than directly looking at gradient descent, we're going to look at an algorithm known as the natural gradient descent. And pretty much all variants in practice do some tricks that are related to this algorithm. So TRPO, many of you have heard of this. This is one of OpenAI's algorithms. That's basically the same thing as the natural gradient. And PPO, you can think of as just a faster way of doing this. But the basic idea is, what's wrong with, what's the annoying thing about using this softmax policy parameterization? Well, the nice thing about using it is, we want to restrict to working in the simplex. So this is a parameterization of the simplex. But the problem is that we're taking the entire real line, squishing it in the simplex, but our contours are all like bunching up near the corners of the simplex because we have e to the theta and this thing in the exponent. Basically, you're going to get very, very flat gradients near the corners of your simplex. Okay, so as your policies become deterministic, you get very flat gradients. So one procedure people like to do in practice is some type of preconditioning approach where you kind of stretch the contours out near the boundary so you can travel much more quickly as things become deterministic. Okay, so rather than directly doing gradient descent, what we're going to do is follow the gradient, but multiply it by this preconditioner, and just think about this as trying to move more quickly near the boundaries of this simplex. So questions about that? This is, this preconditioner is kind of the Fisher matrix that shows up in statistics. Okay. But just geometrically, all you're going to do is try to move more near the corners so you don't get stuck. Okay, so this is the algorithm we're going to look at. And pretty much all the practical variants are either this one or some variant along these lines. Okay, and the motivation is just, from the practical side, was we just want to move faster near the boundaries. Okay, so we're going to look at sort of these different classes under this algorithm and try to understand their convergence rates, will they even converge to the right answer, how they deal with these flat gradient issues, and so on. Okay, so let's start with the softmax class. Okay, so we have one parameter for every state action pair. Okay, so here for this algorithm, you can actually prove that. So now we're going to look at the exact algorithm. So rather than doing these Monte Carlo rollouts, suppose an oracle exactly gave us the gradient. Okay, so this is the simplest possible setting we can deal with. Okay, now we can show we get a convergence rate which is 1 over t. So we run this algorithm for t iterations with a constant learning rate. Okay, and we can show that after t iterations, our value is close to the optimal value by something that's dropping as 1 over t. Okay, and it only depends polynomially on the horizon. Okay, so this is striking for a number of reasons. Okay, so the first is that this iteration complexity is independent of the number of states and actions in the world. Okay, so that's interesting. And of course, it's globally converging on top of that, because this really is not a convex parameterization. But we're showing it's globally converging. And there's no dependence on the number of states and actions. And it's interesting that it's what people call a fast rate. So it's converging like 1 over t and not 1 over root t. So that's also kind of curious. Okay, and it's particularly interesting because this really is not it's really not a convex optimization problem when we parameterize it this way. So why is this working? Well, It's actually related to some connections to an older paper with Yashai Mansour and Ayal Avendar, where there's somehow a connection between this algorithm and a notion of mirror descent. Okay, and I'll leave this more as an open question, but for this tabular case, if you actually just, so let's go back to this update rule. Okay, so now we're going to plug in the Softmax policy parameterization into this update rule. So this is, we take the gradient, and then we do this inverse. And we're going to look at what happens to our policy in the case where the parameterization is the softmax. Okay. So it turns out the update rule is like a soft version of policy iteration. Okay, so the claim is this is the exact way in which your policies are updated under the softmax parameterization. So what you're doing is you take your current probability of taking action A given S, and you're multiplying it by something that's proportional to E to this Q value. Okay, so basically every action, you're boosting its probability by how good it is under this Q function. Okay, and then you're renormalizing. Okay, so think of the case where eta goes to infinity for this update rule. Then this is going to start behaving, then it's exactly the same as policy iteration, so for those of you familiar with dynamic programming. Okay, so it's kind of like a very soft version of policy iteration. Okay, and somehow using this functional form, you can show global convergence, but it's curious that it doesn't look like any type of convex analysis. And so just taking a digression, you might hope that maybe this is tracking the path of some interior point algorithm, and then maybe what's actually going on is it's some convex analysis in disguise, because maybe this is actually following some path of some type of interior within your simplex, and maybe that's what's going on. And I really don't believe that's the case. I mean, we can't prove it's not that, but the natural candidates to check, it doesn't look like that's what's going on. And my gut feeling is that to understand maybe, the proof of this is very short, but what we'd like is a technique that sheds light on this through the lens of how we understand optimization here. And I would argue that this is working partly because of its connections to policy iteration. And policy iteration is one of these algorithms that we don't really have an analysis through convexity. It's almost more like a simplex type of method. But the fact is, this algorithm is actually not sort of bouncing around. It's like a soft version of moving along the path of policy iteration. But somehow that viewpoint doesn't really lead to like a black box procedure to do the analysis. But I think understanding this from some type of interior point perspective might actually be helpful from algorithm design. So if you want to chat, yes, Kostas?
Why do you say it's non-convex?
Okay, so what I mean by non-convex, in this parameterization, it isn't convex. So there's no like black box analysis that you can say, hey, you're running gradient descent, this will converge at a finite rate. So we know how to solve this by rewriting the problem as a convex optimization problem. So for example, a sort of more technical answer, you could think about writing the convex optimization problem in terms of the state action visitation frequencies. Okay, and then you could maybe look at mirror descent in that polytope, but that's not the path you're taking here. Okay, so, and in fact, but that's really the question here. This parameterization is some parameterization, but it's definitely not a convex parameterization, yet we're converging. And the proof is very clean too. So Kostas?
And just to clarify, if you didn't do natural gradient, but you did normal gradient.
Oh my God.
How does this update change?
How does the...
This exponential weights, like is there like...
yeah, then it goes back to... then okay, so then you don't have this exp of q. It's more like you're updating pi of a given s just in proportional to q and in proportion to the current probability of visiting the state.
Okay,
There's some scaling, but that scaling, I think, can make things exponentially slow. Because,
It's more aggressive.
yeah, it's far more aggressive. Like, basically, this update rule is not affected by the chance you're visiting some state. And that's very important, because if you're visiting some state very infrequently, you still need to update it very quickly. Okay? And if you don't do this rescaling, it can be arbitrarily slow. Okay, so.
Does this imply or does this result contain some proximity of the policy to the optimal policy at all? Like in the policy space rather than in the value space? Like do you actually get the entire policy from this?
I mean, this just amounts to questions about kind of the LP kinds of things, because if there's a gap, you'll snap to it. But if there isn't, because your values are close, okay, but then why does your values or your policy being close get the argmin close? Like, just think of it the LP viewpoint. If we know, like, even if I told you the values are close to the optimal policy, we might not snap to one of the optimal policies unless there's some kind of gap.
Sure.
So,
But you get 1/t rate, so
yeah, so we're close in value.
yeah, but since you have fast rates, usually the way you get them by in say context optimization is when you have like a quadratic growth around the minimum, for example.
Yeah,
I
yeah.
was wondering if you actually get that as well in there.
So we can't get the augment. Well, in the smooth case, you want to actually getting close in augment. So a convex function that's smooth, you get a 1/t rate, but you aren't getting close in augment.
Okay.
So yeah, so I don't see how to get augment, but it is curious how we're getting the 1/t, because yeah, it happens, but we don't really have a good understanding. Even though the proof is like, so it's like literally just like mirror descent. You just follow the steps and it works. But yeah, we don't know about. I mean, I don't think you should get augment convergence, because unless there's some kind of gap in the values, right? Like this really should be exponential in bit complexity. Okay, so again, and this is about this really is the best case setting. We're dealing with small states, and we haven't dealt with sample gradients or function approximation. Okay, but at some level, this should be somewhat heartening, because at least the methods we're using in practice aren't breaking in these toy problems if we give it exact gradients. Okay, and we do this preconditioning, which is what people do. So at least we have the sanity check that the methods we're using, when we specialize them to simpler problems, provided we can compute the gradients accurately, everything's fine. Okay, so what about the case of function approximation? Okay, and here I want to touch upon a relationship to how we get robust policies, which is actually related to optimization issues. So let's take a step back and look at robustness. Okay, and the point I'm going to make is that on real systems, if you train your policy to only behave well from one start state, it often leads to very brittle policies when you perturb things. Okay, so here's one of these toy things. We kick this system. So it knows how to get up and hop from one configuration. You kick it, it falls down to a different configuration. It can't get back up. Okay, it's the same thing here. This thing knows how to run. It knows how to get up from one configuration. You knock it over, it can't get back up. Okay, and how do you fix this in practice? Because and what you're going to do in practice is you aren't just going to optimize your policy to do well under one starting state. You're going to actually start your system in many different configurations and try to get it to do well in a broad variety of configurations. Okay, and this is assuming you have the ability to do this. So we're not solving exploration, but what we often need to do is actually we'll literally just start the system in many different configurations. And even this OpenAI thing, this is really what they did. They didn't just train this on one simulator. They kind of trained it starting in many different configurations, and they kind of mixed up all the physics parameters. They call this domain randomization. But they really tried to train it under a very diverse set of starting configurations. And this is important. So it turns out it's at least slightly robust. They had this cute little demo that, you have this giraffe, push it, it can recover, but you need to do this even just to get the system to work, because of, your model isn't good. Okay, so there's a bit of a digression, but it's actually important even for our theoretical analysis, which is if we go back to this example, and if we think about some kind of sampling-based scheme, you're kind of doomed because you're never going to get any kind of accurate gradient here if you're running some kind of Monte Carlo rollout starting at S0 if you act randomly. Okay, so the way you fix this in practice is kind of the same way you fix this robustness issue. Rather than optimizing a value function starting at S0, we're going to optimize a value function with some start state distribution which has coverage over the state space. Okay, so here if this mu measure actually is uniform over the state space, some of the time we're going to start near to where this reward is, and just randomly we'll hit it, and then we'll eventually kind of back propagate the gradients. Eventually we'll figure out what to do there, and we'll propagate things all the way back. Okay? So this is really a cheat, right? Like to get these things to work, we'll often have to cheat and actually initialize the system in lots of different configurations. And this is a user choice, okay? But it's a choice that on the theory side, it's actually how we can avoid some of these worst case guarantees, that somehow based on this choice of measure mu, using a different class of algorithms, we can actually get various non-trivial guarantees. Okay, and there's a kind of a line of work of research arguing why this measure mu is good. But for example, one case that's very intuitive is think about imitation learning. Suppose we actually had an expert that demonstrated us what to do and maybe started us in good configurations. Like, this is a great setting to be in. Okay? Maybe we don't have that, but so the setting we're going to look at now is this more practical setting. Rather than taking gradients at S0, which we know we're doomed by just from this simple example, let's look at a different cost function where we're optimizing our gradients under a different start state measure. Okay. But we still care about how we do at S0. Because note, in this particular case, if we start uniformly, we will actually get the correct policy starting at S0. Okay? And this is really one of the tricks people do in practice. Okay, so for this other cost function, we definitely have some theory for it. But on the other hand, what we do in practice are these gradient-based methods. So what can we say about these gradient-based methods when we have function approximation and we introduce the start state measure mu, which is different from S0? Okay, and it turns out that the guarantees we get are very similar to this the guarantees we got for this older algorithm conservative policy iteration. So let's just look at that. And let's look at what's going to go on in these two cases. So we understood the Softmax policy class. Now let's look at these two policy classes. Okay, and this class is interesting because it's like the simplest generalization of the Softmax case, but now we might not contain the optimal policy. Okay. So might we hope something reasonable to occur? Okay. And it turns out we can get guarantees. Okay, and let's go through what we need to get guarantees here. Okay, so this is a little more subtle. Okay, so the quality of the features actually affect how well the algorithm is going to work. Okay, so the condition is we need for the features is that suppose that in an average case sense, these features give us a good linear approximation to these state action values. Okay, so this is like these features well approximate our value functions. And let's suppose they well approximate the value functions in an average case sense under states and actions visited by our current policy pi. So this is a really great condition because this is like what we might hope to occur in supervised learning, that on average we can well approximate the function. Okay. So that's a nice condition. The second condition is not so great, but those of you familiar with approximate dynamic programming might realize that the guarantees when you do approximate dynamic programming are horribly worst case. And this condition is going to make use of the starting measure mu. So think of this example, we're trying to control the hand. We're going to guess some starting configuration, and the quality of what we find is going to depend on this starting configuration. And we're going to look at the ratio between where a good policy tends to visit and our starting configurations. Okay, so it's a worst case ratio, but the intuition is we want to pick a starting configuration in a way that has support where a good policy tends to visit. Okay, so call that this factor gamma. Okay? And then what we get for this case of using linear policies is that now we're converging at a slower rate. So we're converging to the optimal policy at a rate like 1 over root t. We only logarithmically depend on the number of actions in the MDP. And we have this polynomial horizon dependence. So this is still interesting because there's no dependence on the number of states and actions. Okay, now we shouldn't expect to reach the optimal because there's approximation error. So we're off by some poly h factor. We're off by epsilon. That epsilon doesn't seem too bad because that's an average case guarantee. But now we've got this annoying amplification effect, gamma. So it's a worst case factor, but this worst case factor is still basically better than anything you could get with dynamic programming based approaches. Because if you think about a case like imitation learning, like suppose you really had an expert giving you demonstrations of where good trajectories are, this factor would be 1. But now this actually handles the approximate case. Okay, so we're converging to the right answer at 1 over root t, but then we have a penalty to how rich our policy class is. Okay, and note our guarantee here is with respect to the start state we care about. Okay, so what this says is even if we care about our behavior from one given start state, we still might need to start the system in many different configurations to get the optimization to work out for these policy gradient methods. Okay, which makes some sense because somehow they aren't going to solve this problem of exploration.
So what do you think is the right type of penalty to pay in the function approximation case? You think some of the additive terms could be improved here, or
without?
You're also paying based on like gamma of S0.
Yeah, and that's unfortunate. Like I think in the worst case, it's hard to improve this factor because. Okay, so where is this coming from? So I think this is a good question of trying to understand. So I think the worst case it can't be improved, but there is a question of like if we have some structural assumptions of the MDP, can we improve it? Okay, but on the other hand, we don't really have strong lower bounds here, but at least for the gradient-based methods. For dynamic programming, we do have lower bounds, and there you can't even get guarantees of this form. And so if we did approximate dynamic programming with errors, then you actually just pay the infinity norm errors. And that's much worse. Okay, so I'm not going to directly answer this question, but maybe I'll answer the question of where is this factor coming from in the analysis, which I think gives some intuition for how to improve it. So what's really going on and why this is a pessimistic factor is this factor is really due to transfer learning. Okay, so what's happening is we're fitting this Q function under where we tend to visit. That's basically what this natural gradient algorithm is doing. It's solving some linear system, but at the end of the day, there's some implicit estimation of the Q function under where we're visiting. But what matters is our error with regards to where the optimal policy tends to visit. Okay, so this factor, this gamma, it really comes from a transfer learning effect where we only kind of see our error under where we're visiting, but in a sense what matters is our regression error under where, say, a good policy tends to visit. Okay, and that factor is really just like a worst case transfer learning factor. So this is why, at least for this class of algorithms, there's reason to believe this factor gamma is pessimistic, because if you really could solve, if transfer learning happened to be working, which it actually does in practice, this factor of gamma is going to be much more mild. Okay, and I'll also mention that, again, this is with exact gradients, but here the sample complexity analysis is straightforward because it's easy to get Monte Carlo estimates of these gradients and include the sample complexity, which is polynomial in epsilon and h. Okay, so it's pretty straightforward to get the sample complexity analysis. So questions about the linear function approximation case? Yes, Kostas?
So, for the previous case, the completely parameterized one,
Yeah.
you showed us that MPG boils down to exponential
Yes.
weights. So, what does this boil down to?
Yeah, good question. So, right, okay, so here's a simple way to think about it. What this boils down to when you reparameterize it is, okay, so, okay, this is exactly the right question. Why did I show that site? Okay, so Chris is saying for the exact case, this is what this update rule boils down to. So what does NPG boil down to the linear function approximation case? Okay, so any guesses? So probably going to replace Q with something.
Gradient.
Well, we're going to replace Q with a regression with the features W. So with the features phi.
Logistic regression? Or?
No, so our function class is e to the w dot phi. Okay, but what we're going to do is, so here's an equivalent way to run the NPG algorithm. Take your features phi, use them to fit your current Q functions. Okay, so now I've got an estimate of my Q functions, and I just put that in to this expression. So I'm updating A given S by e to the w dot phi. So that's what's happening. Okay, and that question kind of gives light as to where this approximation condition is coming from, because it's sort of how well we're accurately estimating those Qs. So what this linear function approximation algorithm is doing is basically, it's basically like a soft version of approximate policy iteration, that you fit your Qs under where you're visiting, okay, and then you plug in your estimated Qs into that algorithm. Okay. But it turns out what's nice here is everything somehow lives in your parameter space theta. So you don't have to explicitly keep around this big table. But that's why the analysis is nice here, because once you understand the exact case, we can think about the approximate cases as just introducing error into the exact case. Okay. And once you see that, that question's a perfect lead-in, so I have to wrap up in a moment, into the neural case. So in the neural case, instead of having a policy that's, in the neural case, rather than our policy being linear in some features, we just have some crazy neural network, which specifies the function in the exponent. All you do for the approximation condition is you just need, the derivative of your gradients to well approximate the Qs, and you get the same guarantees in this case, which is pretty natural, because what does it mean? I want my neural networks such that they're rich in the sense that their gradients are a good function approximator. Okay. And that's a pretty natural connection, and it just immediately follows through with the same analysis. So
why is it not f theta that you want to approximate q pi theta?
f theta is a scalar in a sense.
Okay.
So think of the linear case, right? F theta was w dot phi. If I take the derivative with respect to the parameters w, you get phi. So the linear is just a special case here. Yeah, so it's basically, like in a sense, it's like the direction you're moving in, you want it to somehow well approximate the unconstrained direction. And that's something to do with how rich your policy class is. So it's really just a Taylor's theorem argument. I think if you just understand the linear case, the more general one's clear. But then you can play the usual, you can play the NTK trick. So there's some work by others with the NTK trick, and you can do this for neural network in this, this tangent kernel regime. Okay, so let me just wrap up in that, look, these gradient methods are one of the fundamental tools in RL because they're very robust. And, and I think this work is really helping laying some foundations for what's actually going on both in the approximate regimes and the exact regimes for these methods. And a lot of the issues we face is that the issues in RL are really pretty different from supervised learning, both in terms of estimation, the saddle point behavior, and so on. And at least for me, one of the nice things about working in reinforcement learning is that better algorithms are really needed here, because like in a lot of the cases of supervised learning, it feels very explanatory that we know the right set of algorithms. We just run gradient descent on a cost function. But in RL, we actually need better algorithms because this choice of mu, there's a lot of, it's not obvious how to pick this in real problems. And in harder problems in RL, we're trying to actually deal with exploration. So sometimes we do various other tricks because we can't actually set the agent down in any given location. So we need some way of actually putting exploration in the setting. And we also have this question that there's just a lot of new theoretical questions here that are relevant, that if we could understand transfer learning better, I think that would help in understanding what's going on in reinforcement learning, because somehow in RL, you can kind of only figure out what to do in places you've seen, but why is this generalizing in cases where you've got this uncountably infinite state space? And clearly, where you want to be is a different distribution. Okay, so there's a lot of things about transfer learning that are very relevant for the RL problem as well. So thank you very much.